Let's look at molecular orbitals. If we start with n, or a certain number of atomic orbitals, they'll combine to form the same number n of molecular orbitals. If they form bonding orbitals, those will be lower energy. If they form antibonding orbitals, they'll be higher energy than the original atomic orbitals used to form them. Now, if there are more bonding interactions than antibonding, that will make bonding orbitals. However, if there are more antibonding interactions than bonding within a given orbital, that will form an antibonding orbital. And if the number of bonding interactions and antibonding interactions are equal, then it becomes a non-bonding orbital. So if we look at an example with two p orbitals, the two phases could overlap in the two p orbitals, which would cause them to be attracted to one another. We could draw it this way. Where they both have the same phase. So those are attracted to each other, and that would be lower energy, and that would be called a bonding orbital. And this is a pi bond, so it's a pi bonding orbital, where the same phases overlap. Okay, there also could be an example with those two, where the phases don't overlap, but they're opposite. And those now push apart from each other, and this would be called a pi antibonding orbital. Sometimes it's abbreviated by an asterisk. We'll call it pi star. So we would call this orbital pi and this one pi star. So this is the pi bonding orbital, this is the pi antibonding orbital. So when we put our two atomic orbitals together, we end up with two molecular orbitals, one bonding, one antibonding. And if you want to think about what they might look like, the bonding one has all the electron density shared between the two, while the antibonding one, they're pushing away from each other. The orbitals are actually pushing outside of the bond area. Now we have to fill in the electrons. We have two electrons, and they have choices of where to go. Of course, electrons always go to the lowest energy. So I start down here, and each orbital can hold two electrons. So if I fill in my two electrons, they would both be in the pi bonding orbital, and there would be no electrons in the pi antibonding orbital. So this is why this bond forms. You've got two atomic orbitals that come together, they form two molecular orbitals, and the lowest energy place for those electrons to be is in the pi bonding orbital. Now let's look at the pi molecular orbitals of benzene, which are formed from 6 p orbitals. So the 6 p orbitals will overlap to form 6 new molecular orbitals. So we'll start with drawing what's the most stable one going to be, the one with the most bonding interactions. So the one with the most bonding interactions is the one where these all have the same phase. So every interaction from each orbital to the next is all a bonding interaction. So this orbital would have 6 bonding interactions, 0 antibonding interactions, so it has 6 net bonds. So this is going to be a bonding molecular orbital. Let's go up to the next level, and it turns out at the next level there are actually 2 different ways that we can draw this next one that both have the same energy. So let's see why. So if I look here, I have a bonding interaction between these two, I have a bonding interaction between those two, I have a bonding interaction here, and I have a bonding interaction there. So I have 4 bonding interactions. Remember, that's because they have the same phase. But I also have an antibonding interaction there and an antibonding interaction there. So I have 2 antibonding interactions. So we actually just do math. That's sort of simple math, and say, well, if we have 4 bonds and 2 antibonds, the 2 antibonds cancel out 2 of the bonds, so I have 2 net bonds in this interaction. So this, again, is a bonding orbital. Now there's another way that we can actually get 2 net bonds. And to do that, we end up having 2 of the orbitals are called null, or there's 0 electron density there. So this one and this one don't have any electron density shown in this molecular orbital. So if I draw it like this, I have a bonding interaction between these two. I have a bonding interaction between those two. There are no interactions going to either side because there is no orbital there. So this has also 2 net bonds. Since it has the exact same number of bonds as this other one, it's at the exact same energy level. They both have 2 net bonds, or 2 net bonding interactions, and so they're at the same energy level. So if I go up to the next energy level, I have a bonding interaction between these two, a bonding interaction between these two. I have an antibonding interaction there, antibonding, antibonding, and antibonding. So here I have 2 bonds. I have 4 antibonds. So my net here is going to be 2 net antibonds, or antibonding interactions. So this orbital is going to be an antibonding orbital. So it's going to be higher in energy than the original ones. If you notice, these first 3 I've drawn are all lower in energy than the initial 6 p orbitals that we started with. Now we're going to be moving in higher energy than the p orbitals that we started with. These are antibonding interactions, or antibonding orbitals. Whether you could guess it or not, there is another orbital that we can draw that has the same energy as that one. It's similar to the last one in that it has 2 null sets. In this example, there's an antibonding interaction here and an antibonding interaction there. There's null orbitals at each of these places, which means there's no orbital there, so there's no interaction going across here. So this has 2 antibonds, 0 bonds, for a net of 2 antibonds. So it's the exact same as the other one over here, has a net of 2 antibonding interactions. So this one here has an antibonding interaction, antibonding, 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 all the way around. So this one has 0 bonding interactions, 6 antibonding interactions, for a net of 6 antibonding interactions. So again, this is going to be an antibonding orbital. So when we name these orbitals, we'll usually name these like psi 1, psi 2, psi 3, psi star 4, to signify that's an antibonding orbital, psi star 5, and psi star 6. Now, anytime there's a level that has more than one orbital at that level, those orbitals are called degenerate. It means that they're of the same energy. Then the last thing to do is to fill in the electrons. So we started with 6 pi electrons out here, and then we need to fill in 6 electrons in the molecular orbitals. So there are 6 in atomic orbitals, there need to be 6 in the molecular orbitals. So if we're going to start filling electrons, all you do is you go to the bottom and start filling your way up until you've used up all your electrons. So 1, 2, each orbital can only hold 2 electrons. 3, 4, since they're degenerate, we get 1 in each orbital first before they match up. 5, 6. We're all out of electrons. All of our electrons are in stabilized bonding orbitals. We have no electrons up here in antibonding orbitals. The lowered energy of these electrons by going into these bonding orbitals is what makes benzene so particularly stable. Now there's another way to look at energy in addition to this, is we can look at what are called nodes. In a node, there's a change of phase between the orbitals. So if I look here at the lowest energy one, there are actually no nodes. They have the same phase all the way around. However, if I look here, there's a node. Between here and here, there's a phase change. Between there and there's a phase change. So at this level, there's 1 node. At this level, there are 0 nodes. The same you can show here is that there's 1 node here. The difference, though, is that the node actually passes through these 2 carbons, and that's why their orbitals are null, or there's no orbital drawn there, because it's on a node. There's no electron density at that point. This one also has 1 node. Right, so you can see this as the energy goes up. At the bottom, there are 0 nodes. These 2 have 1 node. They both have 2 net bonds also. So then we go up to the next level, and if we look here, there's a node going through here, and there's another node going through this way. So now there are 2 nodes. right? And that's going to be higher energy. And the same is true here. There's one node here going through the 2 carbon atoms, which is, again, why they're null. And there's another node here going between them. 2 nodes. And then for the highest energy one, there's one node going through here, there's one node going through there, and there's a third node going through here. There are 3 nodes. That's what makes that the highest energy.